hybrid deep learning model for prediction of structural damage. Contents of the video. Problem statement. Structural damage detection has been an area of interest in the recent years to propose techniques that could detect anomalies in the structures caused due to vibrations affecting their stiffness, stability and reducing their life. The techniques discovered so far involves application of machine learning algorithms to automate this process of monitoring the structure's health, which requires manually selecting the relevant features, demanding an expertise in the domain and often failing to recognize underlying patterns. This seemingly impossible task of selecting the relevant features can be dealt with the application of deep learning techniques instead of prevailing machine learning techniques. Solution to the problem. First, to fulfill the demand of data, a G+20 building is designed consisting of a ground floor, 19 upper floors and 1 terrace. G+20 buildings are suitable for such studies considering the fact that such buildings are designed to handle gravity loads, improve ductility of the structure without compromising the stiffness and resistivity to displacements in the structure. Second, different scales of acceleration is used to simulate the vibrations of earthquakes to imitate the real-world scenarios in the structure, as stated here, along the x and y axes of the accelerometer, and the data is recorded. Third, feature extraction and damage classification of building using artificial neural network like 1D CNNs, long short-term memory, LSTMs, 2D CNNs. An ensembled network is done by training on the simulated data created using the design structure. Here is a modeled structure. Methodology. First, the data recorded for different axes, x and y axes, were appended to form a sequence of 8002 timestamps, 4001 timestamps for each axis. These appended sequences were now segregated into training and validation sets, containing 60 and 16 sequences of vibrational data each for the 440 joints of the structure. In this way, 440 different networks are trained for the 440 joints present in the structure designed for the study, and the results, that is probability of damage, from each network are averaged to calculate the average probability of damage for the structure. The equation for average probability of damage of a structure is described here, where the number of joints in the design structure is 440. The network processes the input accelerometer signals for a joint and determine whether the joint has been damaged or not, that is, hinge has been formed or not, by calculating the probability of damage. These probabilities of damage are applied in equation 1 to calculate the average probability of damage. 1D CNN. In this application of 1D CNNs, it is found that a sequence of TANH and RLU activation function providing the necessary nonlinear transformations to learn. The input layer has TANH function, TIN layer has RLU function, while the output layer has sigmoid function. Stochastic gradient descent optimizer ADAM has been used. After segregating the database into training and testing sets, as described in methodology, this data was now reshaped as an array of shape, number of samples, 4001, 2. Purpose of choosing this shape was the fact that our data comprised of readings from two different axes, x and y, hence two channels of 4001 readings each to extract features from both the axes simultaneously. 1D CNN layers. Long short-term memory, LSTM. These networks have loops in them that provides the property of persistence compared to other traditional networks and could be beneficial in extracting the repetitive features in the vibrational data. A dropout layer with the rate of 0.2 has been added after the first LSTM cell and another after the hidden dense layer to avoid overfitting. The activation function TANH is used in the input layer, RLU is used in the hidden dense layer, and activation function softmax is used in output layer. The optimizer ADAM is used. 100 units were selected for the input layer to optimize the training results. LSTM layers. 2D CNN. First, the dataset is produced, which is in the form of spectrograms that will be used as the input for training and testing purposes from the same vibrational data that was collected from the accelerometers of the designed structure. The images produced possess a resolution of width and height of 432 and 288 pixels respectively, having an approximate size of 33 kilobytes. The input shape of the 2D convolutional neural network is 432 times 288 times 3. Here, 432 times 288 represents the dimension of the image, whereas 3 represents the number of channels being fed into the network. The input layer has a loop activation function which works efficiently to provide nonlinearity, in this case the other activation functions. 64 filters were used during feature extraction process having same kernel size of 3 times 3. Input data is divided into batches of size 4 to avoid the resource exhaustion error encountered during training over large image datasets. Spectrogram input for 2D CNN. 2D CNN layers. 1D CNN and LSTM assembled. The weights of the pre-trained 1D CNN and LSTM were frozen and assembled together, followed by a dense layer with sigmoid activation function. The optimizer atom is used. Structure of the assembled network used and the associated parameters are described in Table 4. 1D CNN and LSTM ensemble layers. Project efficiency. The accuracy of the network in Figure 3 signifies the average probability of damage, calculated from the trained neural networks using the equation 1 described above to predict the structural damage. Number of layers denoted in the legend of Figure 3 signifies the number of respective networks layers used for the purpose of training and predicting. The axis of accelerometer in Table 5 denotes the respective axes recordings taken to feed into network. Experimental results. Project reliability. LSTMs and 1D CNNs, that feeds on frequency-based vibrational data directly from the accelerometers, does not require such additional hardwares and are relatively easy to be deployed to industrial applications or devices with minimal computational efficiency and battery power, thus making them a suitable choice for any such application in future. LSTMs performs better than all the other neural networks that have been used in the project, and its significantly high accuracy tends to point out the sequential nature of the earthquake's vibrational data from accelerometers, a domain of signals where LSTMs are known to outperform other networks. This might indicate a presence of sequence or underlying sequential patterns. Therefore, this project and its data might prove to be useful in applications dealing with the prediction and prevention of damages from earthquakes in the future.